All right, class, let's get this going. So today we are looking at Lewis dot structures and Lewis structures and how they describe covalently bonded compounds. And we'll then be expanding on that and looking at resonance. But today is just on Lewis dot structures, how they're formed, how we make them. And they basically represent where the electrons are involved in bonding and non-bonding electrons. And we're, of course, talking about valence electrons, outer shell electrons that influence the way that other atoms combine or interact with each other. So first step in writing a Lewis structure is tally up the total number of valence electrons for all the atoms in a structure. So find the sum of valence electrons of all atoms in the polyatomic ion or molecule. So we'll do Lewis dot structures for ions as well as molecules. If it's an anion, remember to add additional electrons according to the negative charge that the compound has. If it's a cation, you want to make sure to subtract that. So, like, let's say you're going to do the Lewis dot structure for phosphate, which is PO4 3 minus. So you're going to tally up the phosphorus, which is 5, and then for 4 oxygens, it's going to be 4 times 6, and then you're also going to add 3 more electrons because the phosphate ion has a negative 3 charge. Next, what you're going to do is you are going to pick the central atom from the compound, and it's typically going to be, it will be the least electronegative element is put in the middle, unless it's hydrogen, and then it's not going to be hydrogen. But the least electronegative. So you have that table of electronegativities in your textbook, and it really goes through, you can just kind of use the trends on the periodic table to determine what's going to be your central atom. And often it's the single atom that's included, and when you write a covalently bonded formula, the lowest electronegativity is always written first in the formula's name. So next, okay, so once you have your central atom, you are then going to surround your central atom with your other atoms and connect them with single bonds, so single lines. And each single line represents 2 electrons. So you've now used up, in our example here, you've used up 6 electrons. So we have 20 electrons left. And we just want to keep track of those as we're going along. Next, we want to fill the octets of all the outer electrons, or all the outer atoms. So all those chlorines now have 6 or 3 pairs, 6 electrons out there. We've used 18, so we have 2 left. And then you want to fill the octet of the central atom. And in this example, the whole thing is filled and we're good to go. Now, let's say we have an example where we run out of electrons before we can put electrons in the central atom. So that's when you start making multiple bonds so that all of the atoms fill their octet. Our example here, we have the carbon and the nitrogen bond, only a single bond. The nitrogen then shares 2 pairs of electrons, making a triple bond between the carbon and the nitrogen, and thus completing the octet of both nitrogen and carbon. To predict whether or not one electron configuration is better than another, you can assign formal charges to the different atoms and then equate whether or not they and predict which one is more predictable. Having a low formal charge is better than having a high formal charge. So your example being here, so we've got this carbon dioxide Lewis dot structure, or Lewis structure, and 2 versions. Okay, one where you have 2 double bonds on the carbon, and then one where you have a triple and a single. Both ways follow the octet, and so by doing the formal charges, we can get a better idea of which one is the most likely structure. So to do this, you want to count the electrons in lone pairs and half the electrons it shares with other atoms. So if it's a double bond, then it gets half of that share. And so for the carbon dioxide Lewis structure that has 2 double bonds, the formal charge is 0 across the board, where the other one has one's a -1, the other one's a +1. So the one where the carbon dioxide has 2 double bonds is the favorable structure, or the most likely structure using formal charges. So like I said, the best Lewis structure is the one with the fewest charges. So we've got 3 examples here, and we've got one where it's a -2, 0, +1, and then the second one is -1, 0, 0, the other one is 0, 0, -1. So the best Lewis structure is the one with the fewest charges and puts a negative charge on the most electronegative atom. So between the two, so we've got 3 different structures for a carbon oxygen, or I guess a carbon nitrogen oxygen molecule. The first one has a lot of charges, so we're going to throw them out. The second one here has a -1 formal charge on the nitrogen and a 0 and 0 on the carbon and the oxygen. Now, oxygen is more electronegative than nitrogen, so the last structure is our most favorable because the formal charge is on the most electronegative oxygen. So we're going to pick that one as our best Lewis structure for this compound. And then tomorrow we'll get into resonance. So please finish these notes and get your homework done from today, and we'll see you.